Hello, everyone. Welcome to the first Blue Sky session. My name is Jay from Google, and I'm one of the session chairs.
Hi, everyone. My name is Chelsea Finn. I am an assistant professor at Stanford, and I'm the other Blue Sky session chair. The Blue Sky sessions are a new addition to Coral this year. There was a call for papers that are different than the standard contributed papers. They are papers that are meant to take a position, maybe a position that's controversial, maybe a position about where they think the future of robotic learning should be. And so really the intention of this session and the other Blue Sky sessions is to spur a discussion and talk about where the future research should go. With that, I definitely encourage you to ask questions. We'll have 5 papers in this session. And so we'll have 5-minute talks from each of those speakers. And at the end, we'll have about 30 minutes for Q&A and discussion. For people who are live, you can raise your hand to ask a question. And for people who are virtual, you can enter your questions on FeedLoop.
Okay, without further ado, let's start with our first presentation. The first presentation is given by Ed. He's going to talk about back to reality for imitation learning.
All right, hey everyone. Let's see. Who's that? That's not me. Have I changed? Okay. So I wanted to start my talk with a question to the audience, ask you guys for your opinion. And I want you to think of your answer, and then I'm going to ask you to put your hands up, okay? So my question is, how do you define robot learning? And I'm going to give you 2 options, and I want to see, I'm just interested to survey the room. You can play along at home as well. And I just want to see what your response is to this question. So I'm going to give you 2 options. So the first option is you define robot learning as the study of machine learning methods for applications to robotics. The second is that you define robot learning as the study of methods that enable robots to learn. So there's a slight subtle difference there. Just have a look at those, and I'll ask you in a moment to put your hand out and tell me which one you agree with. Okay, so please put your hand up if you think that robot learning is the study of machine learning methods for applications to robotics. Okay, about 10 people. Okay, very brave. Put your hand up if you think that robot learning should be the study of methods that enable robots to learn. Okay, so you guys, most of you agree with me. Okay, but the way I see it is that actually the way our evaluation metrics are set up is that actually it's as if we agree with the first statement, okay? What I mean by this is the first statement is really saying, okay, we should be data efficient. The second statement is saying we should be time efficient, okay? So robot learning really emerged from machine learning rather than robotics, the way I see it, because of developments in deep learning and reinforcement learning. And so we've carried with us those same evaluation metrics on data efficiency. But when we think about real-world robotics, actually what we care about is the amount of time that it takes a robot to learn a task. So let's have a look at data efficiency. So with machine learning, it makes a lot of sense to evaluate with data efficiency because the total amount of data that you collect is kind of proportional to the amount of time. You know, the amount of data you collect is going to take longer to label that data, and then you train on that data, okay? But with robotics, and particularly imitation learning, the total time is much more complex. It's multi-factor. So we have the amount of time that the robot spends collecting data through exploration. We have the amount of time that human spends providing demos. And then we also have this sort of human supervision time, which is this extra component. So the robot time and the human demos, those are incorporated in the amount of data that a method needs. But the human supervision on top of all that is not incorporated into the data efficiency. And I think this is problematic. So let's go through a worked example. So let's say the time for one demonstration, the clock time, is about the same time as time for one environment reset. So let's say you wanted to teach a robot how to stack a cube or not stack 2 cubes together. Then we need to, we can say that the amount of time to provide a demonstration is the same amount of time to reset the environment when the robot fails. But from one demonstration, you get, let's say, 100 samples, and from one environment reset, you get 0 samples, okay? I'm just going to press the button. That doesn't work. Okay. So according to the data efficiency metric, 1 demonstration and 100 environment resets is better than 2 demonstrations and 10 environment resets, assuming the same performance and the same amount of robot exploration. And what we're doing at the moment is encouraging the top method to be developed. But I would rather, as a human, I would rather have the second method, the bottom method. So I'd rather provide 2 demonstrations and 10 environment resets than 1 demonstration and 100 environment resets, because I want to be lazy. You know, I don't want to have to spend time teaching the robot. Let's look at another example. So this is a typical graph that you might see in machine learning communities, but also a lot of papers here at Coral will have these kinds of graphs. The x-axis is the amount of data, so that would be amount of data, number of episodes, let's say, or number of transitions. The y-axis is the success rate. And we can see here that everybody would assume that the red method is better than the blue method. But let's see what happens when we take this into reality with robotics. And we start considering time efficiency. Well, let's imagine that the blue method is, the time is proportional to the data. What happens with the red method if you need ground truth object poses, let's say, which is something that simulators often assume? Well, actually, you've got to go through this period of training that object pose estimator. And I think that's fine, you know, training an object pose estimator and then getting the robot to learn from those poses is okay, but we should be incorporating that into our evaluation. And then you could say, well, actually, the red method is still better because in the long term, it's going to overtake the blue method, all right? But what if there's some period of reinforcement learning that requires a human to continually reset the environment? In that case, actually, the red graph will look like this, and it will be actually very, very inefficient in terms of time because the human has to spend a lot of time supervising the robot, whereas the blue method remains very time efficient. So at the moment, we're encouraging people to develop the blue method. So we're encouraging people to develop the red method. What I want to encourage through this paper is for all of us to develop the blue method. And we need to rethink our benchmarks, so particularly simulation benchmarks. We need to be incorporating the real cost to humans. So we need to add on time every time there's an environment reset. We need to model things like, you know, if we need poses, then let's add on a fixed amount of time that it would take to train that pose estimator. And then I think we would be in a situation where we're actually optimizing for the true cost to humans. And this has inspired the kind of work that we're doing in my lab at the moment. So here's some videos of a method we've developed where what we're trying to do is optimize for the amount of time a human spends supervising. So all of these methods are trained with about 5 seconds of human demonstration time, and that's it. So we just have 1 demonstration, no environment resetting, no prior object knowledge, and no pre-training. And it's the same method, no hyperparameter tuning. The same method works on all these tasks. And I'm doing a demo of this afternoon, so come along and say hi and take a look at the results. So that's my pitch for how to go back to reality for imitation learning, and thanks for listening.
Our next talk is given by Chad, who is going to talk about towards robot that learns to summarize their actions in natural language. And this is going to be a virtual presentation.
Hi, I hope this is working. It's nice to sort of be with you all. So in the future, robots are going to be doing more and more long horizon tasks. They're going to be operating over long periods of time, and they're going to be operating outside geographically of human users. And so they're going to be very hard to supervise. So, you know, the human can't just follow them around and watch what they're doing. So realistically, we're going to be dependent on the robots to tell us what they've done. And so, because it's going to be important to know what the robots are doing. And so we suggest that it would be most useful for humans if the way that the robots told us what they did was in the form of natural language summaries. And so we've broken the idea of natural language summaries into a few tasks. So the first sort of simplest task, although it's not really simple at all, is just giving a pure summarization. And so this is difficult because the summaries, in order to be useful, have to meet a few criteria. So first, they have to be succinct. The summaries can't, the robots can't just tell you everything they've done. They have to pick out the most important things they've done. And then they can't even tell you those either. They have to sort of abstract and give you a higher level, more conceptual summary of what they did. But at the same time, and somewhat in tension with that, the summaries have to be thorough. So they have to tell you everything important that happened. So for example, if a self-driving delivery vehicle came back and said that it had delivered 20 pizzas, but it didn't mention that it ran over one of the customer's dogs, that would be a problem. The summaries have to be context aware. So for some users and in certain circumstances, what will be important to include in the summary will be different. And in some cases, the robot will have to tell you what it did not do, because that might be as important as what it did. A little more complicated is giving an explanation of the robot's past action. So not just what did it do, but why did it do it? And so this we think would be particularly useful in two cases. The first is when there's a failure of some kind. So if the robot was unable to perform one of the tasks it was supposed to perform, it should be able to tell us, was that a malfunction? Was it because something was missing in the environment? Something like that. Would be also useful in the case where choices had to be made. So if the robot in the course of its action had to take a certain route or choose one thing to do over another, it would be useful if it could tell us why it did that. After the robot gives a summary of what it did, it should be able to answer natural language questions about that summary. And so these could be simple clarification questions. So after the robot has given the very high level version of what it did, you may want to know the low level details of what actually happened. And so the robot is going to have to be able to map back from its high level description down to the low level actions. You may ask for an explanation. You may also have unexpected questions. So you may want to know something about the environment that the robot was operating in while it was performing its action. And so it's going to have to learn how to remember things about that it isn't planning to include in its summary. For example, while you were mowing the lawn, did you see the dog? Something like that. We suggest that it will be really important for robots to be able to learn from feedback that they get just to the summaries. So we think this will be particularly useful in lifelong learning settings where we want to deploy a robot in the world and then have it be able to fine-tune its behavior in response to the user feedback. And so the user doesn't want to enter in new code in response to the summary. It doesn't want to call the manufacturer and complain. It just wants to be able to say, oh, you shouldn't have done that. Next time, do it like this. And so the robot needs to be able to map that kind of feedback through its summary back into the actions and the policies that led to those actions. And it should be able to do that ideally from one correction. The first time the robot says it forgot to let in the dog all day, and you tell it next, remember to do that, it shouldn't have to be told twice. Finally, we suggest that we should investigate how the ability to remember and summarize past actions could be used as a way to improve the robot's performance on a variety of tasks. And so if the robot is able to describe its actions at high and low levels in a way that makes sense to humans, then maybe that can be used to get the robot to also perform actions that make sense to humans and that are in alignment with the sorts of things we want them to do. And so this, we think, could be potentially useful in new environments where if the robot already has a sense of the kind of things that humans like to hear about in summaries, this may help the robot attend to useful aspects of a new environment that it's placed in. And if a robot is able to go back and forth between a low-level description of its actions and high-level summaries, this may help it compose new actions out of lower-level behaviors. So thank you. And this was work done with Daniel Bauer.
And our next talk is the task specification problem. Will be given by Pulkit Agrawal. And it's also a remote presentation.
Can you see my screen?
Yes.
Perfect. So today I'm going to talk about the task specification problem. So consider a trained robotic agent, which when deployed, either is unable to perform the task or fails to generalize. The primary conjecture of this talk is that the reason for failure is under specification. That is a situation where a problem admits many equally good solutions. Now, there are many methods designed to overcome under specification. For example, priors, regularization, feature learning, etc. However, as we will see, even these suffer from under specification, which makes this problem particularly challenging. Let's dig into this. And suppose we want to train this agent to walk, and we provide a reward, which is velocity along the x-axis. If we optimize this, what we find is the agent goes towards the right, not by walking, but by sliding on the ground. Why is this? Because the reward function admits multiple solutions. That is, it is under-specified. Right? So maybe we can overcome under-specification by showing the robot the desired behavior. For example, over here, there are many things happening, right? I mean, the table is moving around, the person is moving the bottle, the beaker is moving, the hand is moving, and the person is also pouring water, right? So what is the intent of this demonstration? Just by looking at this video, it is under-specified, right? How do we mitigate this? And so one way to mitigate is to provide a lot of demonstrations and hope that by crunching these diverse data, the agent can learn the correct intent. The other alternative is to say, well, if the agent can reason in terms of relevant features, it might be easier to identify intent. But then the question becomes, what are good features? Which leads us to the question of feature learning. A popular idea for feature learning is to convert the data or compress it into a low-dimensional feature space in the hope that we will learn some independent factors of variation. For example, if we have images, the hope is that we could learn shape, color, and lighting. The problem, however, is that there are multiple different features which are also disentangled. For example, JPEG compression. Right? It's an equally good solution because it also produces a disentangled feature space. So if you were just trying to disentangle, we could either learn a desired solution or we could learn an unwanted solution, right? And we really don't have any ways to control which solution will emerge. Right? So essentially what is happening is, if we are trying to minimize a loss function L, and we are searching through a space of hypotheses, there are multiple optimal hypotheses, and humans and DNNs are finding different solutions, which means that they generalize in different ways, which leads to the kind of issues that we have seen. So one question you might ask is, how do we make them similar? Well, typically, this is a role of regularization. But the question is, what is a good regularizer, right? And the problem is, as we have seen before, that even concepts such as disentanglement do not help us overcome under specification. Another perspective is, maybe what we really care about are features or solutions that work for future tasks. So maybe meta-learning can help us or rescue us from this problem, right? Because meta-learning finds features which can be easily adapted to future tasks. However, even meta-learning requires the knowledge of test time distribution, which is essentially specified by humans, and enumerating all possible future tasks is challenging. Therefore, even these approaches cannot fundamentally escape under specification. Right? So one might say, well, if you're really trying to align the human solution and the neural network solution, why not build in priors such as objects, 3D, and so on that humans use? But even this poses a problem. For example, let's assume we want to build in the prior of an object. Right? The question is, what is an object? Like, consider I tell you a task that I want to move all the candies. Then the bowl and the candies constitute an object. But now suppose I say, give me a candy. Right now, each candy becomes an object. But if I now say, suppose I want to eat the candy, then the candy and the candy wrapper become two distinct objects. So in a way, depending on what the task we are trying to solve, the definition of object is changing. Similarly, if you consider 3D, it is depth when you want to avoid collisions. It is mesh when you want to render, and it becomes surface normals when we want to do grasping, right? So even these ideas, such as objects and 3D, which we assume are good priors, cannot be defined without a task. right? There may not exist a universal task agnostic representation, right? So in summary, what I've talked about is this problem of underspecification and how it percolates different aspects of robot and machine learning. And the takeaway is that we spend a lot of time focusing on algorithms, but maybe what we should really spend time is on extracting human knowledge, right? And a controversial statement to end this talk is that machine learning, maybe we have a good handle on. We can optimize very complex loss functions. But artificial intelligence is about extracting human knowledge, which we are very bad at. Now, with that, I'm going to end this talk. Thank you, everyone, for listening.
The next speaker will be Michael Furland, and he's going to talk about continuous then discrete, a recommendation for building robot brains. Please take it away.
I think it's not unreasonable to say that machine learning techniques have enabled profound advances in robotic capabilities. I think it's also equally fair to say that many of these techniques are atemporal, which is to say that they either do not have a notion of time, they map values to values, or they have a notion of sequence, but they're assuming some temporal discreteness. A fundamental manifestation of the temporal discreteness is that standard artificial neuron lacks temporal properties. It's purely a function of the input state, not of time. The hope then is that the speed of computation will make up for the fact that the real world is temporally continuous, and this is true, I think, in both recurrent and feed-forward neural networks, but time is necessarily passing between and during layers of computation. The standard assumption that nothing changes in real time between two computational steps is appropriate only if your steps are small compared to the dynamics of the system you're interacting with, and that may not necessarily be the case. Further, this discretization comes at a price. Making atemporal algorithms fast enough to behave responsibly can come at considerable costs of power, volume of computing equipment, and engineering time, either limiting what can be fielded in robots, or building a dependence on remote computing and communications links. So what we're proposing is that the design and characterization of machine learning algorithms should begin with the assumption that they are operating in continuous time and characterize the computations using dynamic systems theory and related approaches, and only once it is thus characterized, then approximate them for the temporally discrete computing hardware that we necessarily have to use for the time being. In the paper, we presented 4 arguments for adopting time-continuous algorithms for robotics, including the notion that it would let machine learning more fully embrace approaches from control theory and related fields. But for the sake of brevity, I'd like to focus right now on what I think is the most pragmatic of reasons, and that is specifically energy efficiency, and then highlight some systems that take advantage of continuous time modeling already. So continuous time modeling can be efficient for 2 reasons. The first is that the computations themselves can be efficient. Work conducted at the Center for Theoretical Neuroscience, where I'm based, by Aaron Volkler et al., found that by characterizing computations as continuous and introducing dynamics into the neurons, the neuron state, that they can result in temporally sparse computation that is analogous to the sparsification that is commonly used in connection matrices. The second is that continuous time modeling lets us program low power electronics. And by that I mean recent work on analog neuromorphic computing. For example, the brain-drop neuromorphic chip has been built with a continuity first approach at its core, and it provides extremely low power computing with the ultimate target, not yet achieved, of the 20-watt power budget roughly of the human brain. Understanding algorithms as being continuous in state and embedded in continuous time makes it easier to program these analog computers. Combined, these approaches means that we can do more AI, learning, whatever, for the same power budget. As to applications, we are already starting to see some benefits from continuous time approaches. Examples include the model SPAWN, which is the world's largest functional brain model, and it relies on the continuous time models of symbolic and subsymbolic processing to execute. The Legendre memory unit is a recurrent neural network that was derived first from modeling recurrent neural networks as continuous time dynamical systems and then discretizing them for standard computing hardware. Currently, the LMU is outperforming transformer networks on some language modeling tasks by about the same kind of margin that transformers improve over LSTMs. Lutter et al. have formulated a continuous time value iteration algorithm that demonstrates robustness in the sim to real transition, and they attribute this in part to the continuous time representation that they use in their work. And Applied Brain Research's adaptive controller Reach, based on the work of Jean-Jacques Latin, started with a continuous time first approach, and it was mapped to Intel's neuromorphic chip, achieving state-of-the-art efficiency and accuracy. So to sum up, we're proposing that ML algorithms for robotics should be designed acknowledging the existing continuous time. We feel there are strong reasons to use this type of modeling, not the least of which is the increased energy efficiency. And there are existing techniques which are already benefiting from continuous time modeling. Further, if we ignore these kinds of algorithms, we may well be limiting the capabilities of future robots. Thank you.
Can you guys see my screen now?
Yes, great.
Okay. Hi, everyone. This is Yichun Geng. I'm a master student at Cornell, and today I want to share our vision decentralized data sharing system with you. This work is in collaboration with some great people at ATLC. Okay, I want to begin with a question. So how should we share data among robots? Let's start with just one robot. Suppose we have a self-driving car from a certain company. According to Intel, one such robot can generate 4 terabytes of data per day. Intel is referring to this as a new oil for the future, and therefore, we may want to utilize this resource by sharing. But such amount of data may be hard to share over the commodity network. Moreover, self-driving car company may have already had a fleet of robots on the road. Each of these cars can generate 4 terabytes of data per day, which further increases the sharing load. To further utilize this new oil, different companies may want to exchange and trade their robotic data. This can make data sharing even harder because robots belong to different organizations. Given this problem, let's review some existing approach for data sharing. The first option is federated learning. With this method, robots learn local data and send gradient updates to the cloud. Since only gradient updates are uploaded, sharing load is typically small and acceptable. Privacy is also addressed here because raw data is kept local. However, federated learning requires uniform machine learning models, but robots at diverse work environments can benefit from specialized models. Also, different companies may want to have proprietary models for their robots. We also have a simpler sharing method with centralized learning. With this method, robots simply upload raw data to the cloud. Because we are sharing raw data, cloud can then assign those data to the trainings of different specialized models. And since the trainings are done at the cloud, we have smaller loads on local GPUs. However, the amount of raw data generated by robots can be huge, and therefore, sharing cost is very high. Uploading raw data to the cloud also brings privacy concerns. These two methods share some common drawbacks as well. They both ignore the actual contents of shared data. And since both methods are centralized, the burden on the cloud is very high. So the question really becomes how to efficiently share only valuable data among robots. We think decentralized approach might be the answer. So let's break down the question into 2 parts and discuss efficiency first. We still have the same setup here. To achieve efficiency, we think data sharing should be scalable with peer-to-peer architecture, which offloads the cloud. Also, data sharing should be fair, and we're talking about bit-turn-like sharing. A peer should benefit and contribute at the same time. And the most important part is data sharing should be selective, which brings us to the next slide. Let's work through our proposed system with the same self-driving car example. For simplicity here, we describe 2 robots as a sender and receiver individually. In the real system, both are senders and receivers at the same time. Here, Robot A operates near Cornell, and this snowy image is from my own dashcam video. Because of its location, Robot A should have known snow very well. However, Robot B operates near Stanford, may have little knowledge about snow. So even snowy data is very common for Robot A. Robot B can still benefit from learning snowy images from the data sharing process. And to let Robot A understand that snowy images are worth sharing, we place a sharing model on the sender side. This sharing model is responsible to predict the usefulness or value of certain data from other robots' fields. Initially, this model is random, but for now, let's assume a good sharing model is given to us. Robot A shares 1 to 5% of its highest value data to peers. After a while, robot has a chance of receiving a snowy image from robot A. Robot B will flag this snowy image as useful. Other peers in the network will also keep updating this indicator. When this snowy image finishes traversing the sharing network, a feedback is generated. Eventually, this info will be relayed back to robot A, and it can adjust its sharing model based on feedbacks from the peers. We have collected dashcam videos from diverse locations. And this dataset will be made open sourced. We're very excited about the idea, and we have mentioned some open questions in our paper. We invite researchers to join us and investigate this problem. Thank you so much for listening, and please contact us if you have any questions.
Great, thank you to all of the Blue Sky speakers. Now we're going to have a Q&A session with everyone. Ed, if you can come up to the stage, and then everyone else will be virtual. If you have a question, please raise your hand. I'll actually start from a virtual question by Andrew Hunt, which is for Ed. Do you have any thoughts with respect to crowdsourced project time, demographics, IRB consent, and labor practices? Yeah, so do you have any thoughts with respect to crowdsourced project time, demographics, IRB consent, and labor practices?
Yeah, it's really difficult when you're you basically got to talk about sort of how do you model humans then in this idea of time efficiency, and that is really problematic. I think the way I see it is you can make a big difference just by I don't know, optimizing sort of optimizing over all humans, and then you can start to, and that will I think make methods much more time efficient in general, and then we can start thinking about, okay, let's optimize for different demographics, let's say. But I think the first step is just saying, well, let's have a rough go at this, a coarse movement towards time efficiency, which can be as simple as just saying, let's add on a little penalty every time you have to reset the environment. And I think later on, then we can start saying, well, let's now optimize these methods for particular applications, particular people. But I think that's in the future. I think it's difficult enough to model an average human. So I think that's the first step, and then later on we can start, modeling different groups of people. Yeah.
Great. Any live questions? Okay, I don't see any live questions yet. I'll start with a question for Chad. So. Robotics is already a pretty hard problem, and you seem to suggest that maybe explanations would make it easier through a number of different mechanisms. I'm curious if you have thoughts on whether it could also make it more difficult by introducing this like extra challenge of explaining what you're doing.
Yes, so thank you for the question. So for sure, I think it would make it more difficult at first to do the training, right? Because how to set up the data set and how to set up the environment so that the robot could learn explanations. I mean, and that's why that was the second task. And the first task, which I think is also difficult, is just the learning how to summarize past actions, because it's going to involve, keeping track of all the percepts and then performing memories and then, condensing them into a summary. But I think my hope is that if we get that working and we get the explanation, the ability to provide explanations actually working, then, on a new task, a robot that is already equipped with these kind of capabilities, I think then it could be easier to train a robot on a new task. But first getting that down is going to be a problem.
Great, that makes a lot of sense. I think there's another virtual question. Again, for Ed. So data efficiency and reinforcement learning for robotics often implies that fewer interactions were required to learn the task, leading to fewer failures. What is your take on handling failures in robot learning when considering time efficiency? Should these be considered as an independent metric?
So should failures So if a robot's learning a task and it fails,
there may also be certain kinds of failures, like some failures may damage the robot, for example.
Yeah, I guess. So you can start, I guess this idea, you can start broadening it out beyond just time and saying, okay, what is, I guess one challenge with this is, we have to define what the true cost is to humans. Like time efficiency is, or time is actually not probably the most pure metric. I don't know what it would be, but it might also incorporate the expense, like how expensive is it in terms of money. So then we can start saying, well, yeah, every time a robot bashes into something and fails, then that's a little bit of time because you have to pay somebody to repair that robot, or you have to buy a new robot. But again, I think these extra components of evaluation metrics could be later on integrated and added onto the sort of time aspect once we've sort of moved away from only thinking about data. And then I think we can start bringing in more specific metrics tailored towards particular applications. If you want to optimize for the amount of money you spend, let's say you're very wealthy and you're lazy, then you might want to spend lots of money and not have to teach your robot for very long. But if you don't have very much money and you don't mind putting a bit of effort into it, then maybe you want to optimize for the price that you will pay in terms of money, even if it means that you have to spend more time teaching the robot. So I think that optimization is multi-factor, and it does, goes back to the first question. It depends on who you are and what you want to optimize for. But I think time is quite a general metric that applies to most people, and I think that could move the field on in a good direction, and it would benefit all robot learning methods.
Great. I think there's a question in the front, Francesco.
Yeah, thanks, Ed. It's actually again for you. Thought-provoking question. If we imagine we have this magic metric that will account for the cost of reset, the cost of setting up an experiment, and so on, it seems to me that the easy solution to optimize that metric would be to just go in sim and forget about anything else, because in sim resets are very easy, cheap, and everything else is much easier. State estimation is given. What is your recipe to avoid that sort of easy solution?
Yeah, well, I think there's a couple of points here. One is, yeah, I've done a lot of sim to real work myself, and I don't want to develop methods based on the assumption that one day sim to real is going to work, because I could spend 10 years working on this and saying, okay, hopefully, Majoko, let's say, is going to start working really well for sim to real. I don't want to place my bets on that, because it might be a waste of time. I think sim to real works very well for images, but for dynamics, I'm not sure. I think you have to go into the real world and then come back and then go backwards and forwards, and that's not really sim to real. The other point is, my paper is really on imitation learning. Imitation learning doesn't really work so well when you think about sim to real transfer, because you've got you're doing a demonstration of a task. You don't have an object model for that object. So then if you want to train on that task in simulation, you've got to, build up a model of that object. You've got to tell the robot what the object is. So sim to real is very good for, I think, other areas of robot learning. So let's say exploration based, where you just want robot to explore and build up a general model of the world, let's say. But I think for imitation learning, it's not so appropriate to sort of say, oh, we can just do everything in simulation, because we simply don't have those objects in the real world which you are demonstrating on. You don't have those models readily available to do simulated training on.
In a sense, just to follow up, are you suggesting to include in the metric as well the time it takes for bridging the sim to real gap, or perhaps building a model of your system in sim somehow? How can we scale that horizontal axis that you had in your picture in order to avoid people just doing sim to real?
I think the thing we should optimize for is how long it takes an everyday person to teach a new task. And I think you can do as much training, as much simulation in the lab in advance, and do all of that. And I think we can kind of discount that. And the thing that's really going to allow robot learning to scale is everyday people in their homes, out in the wild, citizen science kind of projects, people teaching robots when those people don't have expert knowledge about how to code up a reward function, let's say, and they just have to give a demonstration. So I think we should be optimizing for that kind of delta on top of all of the pre-training, rather than optimizing for the pre-training, because that's kind of a fixed cost that can then scale to lots and lots of different tasks. But each individual task, you want to minimize the amount of time in the real world with an everyday user, how long it takes to teach that task. And I think that's the thing that I mean when I say time efficiency. It's that delta for learning each new task.
Thanks.
Great. Before we take another live question, I'm going to transition to a question for Pulkit, which is, I think, actually somewhat related to this. Is you're talking about how human time is kind of more expensive than robot time in some ways. And Pulkit was saying that we should be trying to extract human knowledge, and robots should try to extract human knowledge in order to help solve the task specification problem. But this seems actually in conflict with what you're saying, which is that if we want to extract human knowledge, that probably requires a lot of human supervision. Whereas if the robot just wants to extract knowledge about the world, that might be able to happen in a more autonomous fashion. So I'm curious, Pulkit, if you have any thoughts on this.
So it's a good question. So I don't necessarily, think that they are conflicted, right? So I think what I was suggesting is that we need to extract human knowledge. And the other point is that what we should care about is how much is the overall time that it takes the robot to learn, right? So I think there is some combination of, typically what we do today is, right, we define an objective function and then we leave the robot run. And when the robot has finished training, we come back and see what the robot has done, right? So I think, that could be very data inefficient, but consider an alternative setup where you come in occasionally and you're seeing what the robot is doing, maybe provide a few more demonstrations or biased exploration of the robot, right? Maybe right now the techniques that we have to bias exploration are not very good, but in the future assume that, you can provide some natural language instructions that don't explore here, explore there, right? So I think by actually involving human in the loop, we can, cut even the overall training time, right? So I think it is important to distinguish how much human time is involved and what is the total training time of the system. So my perspective is total training time can be reduced by bringing human in the loop, and that might also help, mitigate the underspecification issue.
Great, that makes sense. Laura.
Thanks. Very thought-provoking questions. This is actually very related, which is, I was wondering what your thoughts are, Ed, or others, on whether we should actually split out like robot time and human time, because one could think of an algorithm that takes a week to train on a robot with no intervention, or takes a day to train with like lots of human intervention. And how should we think about those trade-offs? And so, yeah, curious, Ed, what your thoughts are on this.
Yeah, it's a good question. So in my paper, I talk about this. Again, I think it's like, it depends on what you're optimizing for. Like it's really difficult to define the real world cost, but it may be that you want to optimize for overall time efficiency, or you might want to optimize for human time efficiency. So let's take, let's say you're in a factory and you want to, you've got a product that you want to develop to manufacture, and you want to provide a demonstration for a robot to manufacture this product. It's probably more desirable for that company to just spend a lot of human time, pay a human to really get that robot working with demonstrations, lots of demonstrations, such that the robot can start manufacturing that product really, really quickly. It probably doesn't matter if the human spends 10 seconds or 10 minutes, because, well, they've got to come to work anyway and do those demonstrations. But let's take a domestic robot. You probably don't want to spend 10 minutes teaching the robot. You'd rather do a demonstration, then say, go to bed, wake up, and then in the morning, the robot's learned that task for you, and you've done a very small amount of, used a very small amount of human time, but there's probably a lot of learning going on in the background that the robot's doing, and data that it's collecting, and the overall time taken to train might be longer, but that's probably an optimal point to optimize for consumer robots. And so I think you have to have, I have this graph in my paper of human time efficiency versus overall time efficiency, and there's kind of different points along that graph depending on what the true cost is to you as a person, or your business, or whatever it is you're optimizing for.
Great. Let's move on to a virtual question from Pranag, and this is for Chad. What do you think is a good paradigm to learn all of the summarization in natural language and robotic tasks hand in hand?
So I'm not exactly sure what they mean by paradigm, but I think we can look at the work that's been done in natural language instruction following as kind of an example, because the summarization in natural language is sort of the flip side of instruction following. And so I think, to start off with, we could operate in kind of simulated environments where embodied agents in the simulated environments perform actions that have descriptions with them, and they learn how to do that, and then move to the real world and try to describe in the real world, and then move to environments that they hadn't seen before and test their ability to do that. I'm not sure if that answered the question.
Great. We also have another virtual question, and I think I may have saw a hand up over there, so maybe the mic could go over there. In the meantime, this is for Michael. And this is a question from Pete Florence. Could you help describe what the physical road to continuous time computing might look like for an average robotics researcher? I'm thinking that my images come in discretely at 30 hertz, my robot state is at 200 hertz, and I'd like Linux, GPUs or TPUs, modern deep learning libraries, etc. But large gains in efficiency seem pretty exciting. So could we maybe start simulating continuous time hardware with discrete hardware? And what might the steps look like here?
Right. So I guess the first thing I'd like to say is that we're already on the road to this kind of robotic system. And I'm thinking specifically about the adoption of event cameras, where you're not necessarily getting frames on a clock. You're getting events that arrive asynchronously. Then in terms of what kind of a pipeline we go through now, I would say starting with, for obvious bias reasons, starting with the kind of neural modeling that we're doing in our group to analyze these algorithms and have them update in real time. And then we do run them on discrete hardware by and large. Sometimes we get some neuromorphic hardware, which is not necessarily available off the shelf yet. Although, keep an eye to Intel amongst other companies for those. But that adopting that modeling framework would be the first step. In terms of using legacy algorithms, there are techniques for, and I'm speaking strictly in the sense of spiking neural networks because that's what I do. There may be other physical computing, analog computing that you might want to adopt, but there are techniques for mapping existing neural networks onto spiking neural networks, and we've seen efficiency gains from doing that as well. Yeah, so I think that would be the short answer. I hope that's helpful. I'm sorry, it's more, read the book and use our tools. But I'd be happy to communicate more about that if that would be useful.
Great, let's go to the live question.
Yeah, this is related to the data versus time kind of argument as well, so sorry to pile on that again. I think I agree with most of your arguments, and there's a lot of sort of hidden costs that we should be taking into consideration, and I'd argue maybe it should go to sort of level of or degree of supervision and things like that as well. I think the one thing that fixating on data can give us, particularly in a, for example, reinforcement learning context, is that it means that we're sort of ahead of Moore's law, and sort of any kind of assumptions that we make are not going to be undermined by compute being twice as fast in the next year or so. So from that perspective, it does make sense to me to somewhat consider how much you can squeeze out of one piece of experience rather than one unit of time, which might vary depending on how fast your chip is, right? Do you have some thoughts on how to reconcile this with the sort of time-based perspective?
Yeah, I think so. That's an interesting point. So I guess it's related to the simulation question of simulators get better, computers get better, robots will learn more quickly. That requires sim-to-real transfer, which I want to discount if I can. Then I would say, okay, so maybe there is some kind of, even in the real world, the robot will train, and then there'll be some GPU-based training, and that will get better and better over time. we can still kind of optimize for a point in the future. We can say, right, in 10 years' time, I want to develop a method that's going to be the best, most practical method in 10 years' time. And I think you always have to, as researchers in robotics, you have to say, well, what point in the future am I optimizing my methods for? And that's the reason why we all have different strategies and different opinions and different ideas, because we all kind of optimize at different points in the future. So you might be somebody who's saying, I want a method that's going to work in 5 years' time, and then you're probably going to do a little bit more engineering. Or you can say, I want a method that works in 20 years' time, and then maybe it's a little bit more of an end-to-end learned solution. So I think you can still incorporate, you can sort of extrapolate, like where's the point where you're optimizing for? How fast will computers be by then? And then you can incorporate that into your time efficiency. And the other point is, so computers are getting faster over time, but humans aren't. Okay, we're not really evolving as quickly as computers. So the cost to humans in terms of physical supervision of a robot is not going to be getting less over time. So that's a factor that is always going to be there. We can't sort of say, well, there's no equivalent of faster computers for humans. So that aspect there of the cost of humans in terms of time is always going to be there, and we can't get rid of that. So yeah, I hope that answers your question.
A question related to that is, what are your thoughts on existing offline data sets? Sometimes it might be actually zero time involved to like take an existing data set like ImageNet or an existing robot data set. Do you think that should count as zero? Or, I mean, it's kind of hard if you collected a data set for that paper, but maybe it could be reused in future papers. How do you think that should factor into the cost of the algorithm?
Yeah, so I think sometimes it's a blurry line as to whether something is training or testing, because it could be, you could be testing, well, you could be providing a demonstration at test time and say, well, this is my testing. And then that data itself can then be used for training something else. So it's difficult to define the difference between them there. But I think in terms of what we're actually optimizing for, I would count that as zero cost based on what I was saying before of, it's the delta per new task that we should be optimizing for. We can spend 10 years, if somebody said to me, we've got to spend 10 years collecting data, and then the day after that, every robot can learn each new task in 1 minute. I would say that's great, let's go for that. I wouldn't say that, well, that's 10 years of wasted time, because it's not. It's 10 years of useful time that then minimizes the amount of time we have to spend on each new task.
Great, there's a question up there, Carl.
Yeah, I have a question for the fleet robotics talk, the last talk. So I think in the beginning of this conference, Nando gave a keynote where he argued for saving all data you can whenever you generate it. And I think there is compelling arguments for why that might not be feasible if you generate that much data. But then the risk, if you filter it, is that you might throw away data that you actually, like, it depends on the usefulness, right? Like this was your argument. You need to figure out the usefulness of that data first to decide whether to keep it or not. But you might, like, usefulness is tied to tasks, and you might not already know which tasks you might want to do in the future, right? So usefulness in the current moment might be different from usefulness in the future. And so I was wondering whether you had any thoughts on figuring out a task agnostic way of understanding usefulness of data so that you can make that decision at a lower risk.
Yes, thank you for the question. That's an excellent point. And I think for the data that might be relevant for the future, we can always sit that data on board. And for our system, we just want to like share perhaps data that is relevant for the current task. And also I think different we can adjust our the sharing model based on different tasks if we want. Yeah, I think that is a very good question.
Great, and the usefulness of the data probably also depends on the other tasks that you're training on and what you want to use it for, which might complicate things as well. Any other live questions or virtual questions?
Chelsea.
Yeah, go ahead.
Hi, Pulkit, I've got a question for you. It's Ed here from the first talk. So I'm trying to bridge a gap between my talk and yours. So for the task specification, so in my talk, I was talking a lot about the difference between machine learning and robot learning, and I think there is a big difference there in terms of how we should evaluate those methods. Do you see task specification as something which is particularly problematic in robotics, or do you see it as something that's problematic in machine learning and robotics? Because for me, the way I see it is that in machine learning, particularly supervised learning, if the task is not well defined, it's probably because you've just labeled the data incorrectly, and that's just because people haven't tried very hard at labeling data, and it's less of a fundamental issue than it is in robotics, where actually it is genuinely ambiguous, let's say from a demonstration. So I'm wondering what your thoughts are on that.
I think it's an excellent point, Ed. So I feel like the problem exists both in supervised learning and in robot learning, right? And just to build on that point, right? Suppose if we train our detectors on ImageNet, right? And then if we evaluate them in diverse scenarios in photos taken from the household, which was done by the ObjectNet paper a couple of years back. And what you find is the performance, decreases by 40 to 45%. So even though the label is very clear, like what is a chair and what is not a chair, but training on ImageNet, we learn the concept of a chair on the internet, right? Not what a chair is. And that is why these systems fail, right? So even though, yes, the data we are providing, could be taken from the internet, that data has biases in it. And there is, no clear way in how do we collect the right data, right? So I think it's more about data collection, which becomes really hard, right? And, I think the same issue happens with imitation learning or, any other robot learning technique where, just getting the right data is hard. So I see that the under specification problem applies to supervised learning, it applies to reinforcement learning, it applies to learning from demonstrations, it's just everywhere.
Thanks.
Great. Any final questions before we wrap up? Great. One more question for you, Tong. So you mentioned in the paper that you used game theory to determine the price or evaluation of data, which is pretty interesting. Could you elaborate on that and how you did that?
Yes, thank you for the question. So that is actually one open question that we mentioned. And so the essence of our assurance system is to we need to evaluate the usefulness or the value of a certain data. And using the game theory, there is a recent paper that is called Data Shapley. So in that paper, it mentions that we can evaluate the usefulness or the value of data by measuring how much the machine learning can improve on that certain data. So the players are similar to the data points, and we can. So I think we need to decide which data can improve our models the best so which data is the most useful one, and we want to share that kind of data to other peers. So yeah, and we're trying to if you give me this much improvement on my model, then I can pay you, or I will I can pay you that much of the value for your data. Yeah, so that is kind of the trading and exchanging process that we hope to see in the data sharing process.
Okay, great. We're out of time, so this concludes the session. Let's thank all of our Blue Sky speakers again.